Most people walk right past gold-hosting rock because it doesn't sparkle, it stains on weathered outcrops, especially along quiet trails or dried creek beds. Subtle reddish-brown streaks on quartz-bearing stone often signal iron oxide from mineralized fluids. These faint rust-colored traces are early indicators of hydrothermal alteration, a condition commonly associated with gold deposition. Yet unless you're trained to recognize what these stains mean and what they're staining, you'll likely step over the very evidence that could change your understanding of what lies beneath your feet. Gold rarely appears in nugget form at the surface. Instead, it's embedded microscopically in veins and fractures of quartz-rich host rock, often with sulfides like pyrite or arsenopyrite. The key isn't the presence of quartz alone. Millions of quartz veins are barren, but whether the quartz is part of a hydrothermal system. In gold-bearing systems, quartz will often occur with iron sulfide minerals, sometimes visible as brassy flecks or even faint metallic luster under angled sunlight. These inclusions can oxidize over time, leaving behind iron staining, a signpost for those who know what it means. Even more telling is the context. When you find stained quartz in zones of sheared or fractured rock, especially in belts of greenstone or metamorphosed volcanic terrain, you're seeing the geological aftermath of fluid flow under pressure, conditions favorable for gold deposition. Cracks, breccia textures, and sugary, granular quartz are all textures that suggest active mineralization in the past. A quartz vein that's pristine and glassy is less likely to contain gold than one that's been broken and re-healed multiple times. If you come across this kind of material in the field, resist the urge to break off a piece immediately. First, check the surrounding matrix. Is it hosted in a dark mafic rock or altered schist? Are there signs of limonite, yellow-brown staining, gossan, weathered iron cap, or a sharp transition in rock types nearby? These clues build a case for systematic sampling rather than random collection. Mark the site, photograph the vein orientation, and record any associated features like nearby water flows or elevation changes. The tragedy is that in many gold regions, surface clues have been weathered down or mistaken for common rock. But if you know to look for fractured, iron-stained quartz within structurally disturbed zones, you're already ahead of 90% of casual prospectors. The real question, once you've found such a candidate, is how to tell whether it holds any actual gold or just false hope. That's where visual cues start to give way to weight, magnetism, and concentrated field testing. Most quartz veins feel similar in the hand, light, brittle, and glassy. But gold-bearing rock tells a different tactile story. It often feels denser, heavier than expected for its volume, even without visible metal. This weight-in-hand test, while subjective, becomes more accurate with experience. Pick up two similarly sized rocks, one ordinary quartz, the other suspect, and the difference can be surprisingly noticeable. This weight discrepancy often comes from high sulfide content, which not only suggests mineralization, but physically adds mass. More subtly, gold-hosting rock can appear duller, less vitreous than barren quartz. That's because it often contains finely disseminated sulfides, especially pyrite, giving the rock a greasy or resinous luster rather than a glassy shine. In field conditions, this is easy to miss, particularly when the rock is dusty or sun-bleached. But if you wet the surface or chip it to expose a fresh face, these textural differences become clearer. It's an old prospector's trick. A quick rinse or scratch reveals more than hours of staring. Shape and habit matter too. True mineralized quartz is rarely uniform or symmetrical. Instead, look for irregular veins, pinch-and swell patterns, or chaotic breccia zones, evidence of structural movement during mineral deposition. Rounded pebbles or weathered chunks in creek beds, even if quartz-rich, are far less likely to host intact gold structures than angular, freshly exposed veins in situ. That's why stream beds, while good for panning loose gold, rarely yield the full picture. Another underappreciated sign is the host rock itself. Gold tends to concentrate along lithological contacts, where one rock type meets another, especially if one is more permeable or reactive. For example, a quartz vein cutting through ultramafic rock or metavolcanic flows has a far higher chance of being auriferous than the same vein in granite. The boundary is where pressure, temperature, and chemistry combine to allow gold to precipitate. That's why geologic maps, even simple regional ones, can massively increase your odds. Knowing what formations lie beneath your boots sharpens your eye for veins that matter. In many gold districts, miners historically blasted or trenched these quartz veins to follow them along strike, even if they weren't yet productive. Why? Because if you can track the vein's continuity and it passes the next few diagnostic tests, it might justify a grid sampling campaign or even mechanized excavation. But before going that far, one simple test still beats all others for initial field confirmation: crushing and panning a sample. Just a handful of rock, if handled right, can offer proof of concept without any chemicals or lab gear. And the results of that first crush often shock newcomers. Not because they find gold, but because what they thought was gold vanishes under the pan. It's a harsh lesson, but a necessary one. Real gold doesn't shimmer like glitter when crushed. Most first-time crushers see a pan full of sparkling flecks and assume they've struck pay dirt, only to discover they've captured mica, biotite, or some other low-density mineral that floats easily with the swirls. The giveaway is simple: real gold sticks. It hugs the bottom of the pan, stubbornly resisting motion, even under vigorous agitation. Mica, in contrast, will skitter and flash on the surface, reflecting light at exaggerated angles before lifting off with the water flow. To get this test right, you'll need a few key items: a small sledge or rock hammer, a steel mortar and pestle, and a gold pan or simple battue. The first step is reduction, crushing the sample down to sand or silt size. It's not enough to break it into chunks. The finer the grind, the more gold, if any, you can liberate. This is where many go wrong. Large particles trap gold internally, never letting it show up in the pan. Once pulverized, wash the powder into the pan, add water, and begin a controlled swirl. Heavy minerals will begin to sink. Light ones will float and spill. As you remove lighter material, the heavies concentrate in the pan's bottom crease. Here, among the dark sands, typically magnetite and hematite, you're looking for telltale flashes of yellow. Not brassy or rainbow-hued. Those are often iron sulfides, but soft, buttery yellow with rounded edges and no crystalline structure. Gold in rock is rarely angular. If you're unsure, stop the swirl and tap the pan's edge gently. Gold will move as a unit, sliding slowly. False gold will dance and scatter. If you find nothing, don't assume failure yet. Try running a magnet beneath the pan or directly over your concentrates. Many gold-bearing ores contain magnetic minerals like magnetite and ilmenite. Removing these can clarify what remains and help you read the bottom sands. A neodymium magnet will lift black sands easily. What's left may include small flecks of real gold. Still uncertain? Dry the concentrate and examine it under a loupe. True gold reflects a soft yellow under natural light and doesn't tarnish or flake. For those who find small amounts, what prospectors call colors, it's an encouraging sign but not a payday. A few colors per pan suggests trace gold. It takes hundreds of pans to accumulate even a gram. The goal here is not production but confirmation. If your sample yields gold at all, it justifies further testing. The next step might be to grid sample the area or run a higher volume of crushed rock through a sluice or gravity table. But if your pan reveals nothing, and you're confident you crushed and washed properly, it may be time to question the sample source or your assumptions about what gold-bearing rock looks like. Because sometimes, even promising specimens fail this basic field test. And when that happens, your next tool isn't a hammer, it's a magnet. The magnet test isn't for gold itself. Gold is famously non-magnetic, but for what tends to travel with it. In many gold-hosting environments, especially those shaped by hydrothermal fluids, magnetic minerals serve as proxies. Magnetite, ilmenite, and pyrite often co-occur in altered zones rich in sulfides. Their presence in crushed rock concentrates or even in hand specimens can confirm you're within a mineralized system. even if visible gold hasn't appeared yet. To run this test, all you need is a strong neodymium magnet, preferably mounted on a handle or encased in plastic to prevent direct contact with fine powder. After panning or sieving your crushed material, slowly pass the magnet over the dry residue. Watch closely. True black sand, if magnetite dominant, will leap toward the magnet in a tight clump. Ilmenite may respond more sluggishly, but will still drift toward the field. This behavior helps isolate the magnetic fraction, which can then be removed to improve clarity when scanning for gold. The importance of this step goes beyond visibility. Magnetic response in your sample tells you something about its geologic context. Gold hosted in greenstone belts or iron formation link systems often associates with magnetite and pyrite. In contrast, epithermal veins might yield more non-magnetic gangue like barite or calcite. So the magnet isn't just a cleanup tool. It's a quick geological fingerprint. But false positives remain. One of the most common field misreads is mistaking mica for gold due to its shimmering flakes, especially when light strikes at low angles. Mica is soft, hardness 2.5, flakes easily, and appears in muscovite, silver, or biotite, bronze-black forms. Unlike gold, it floats, splits under pressure, and burns off under high heat. A simple thumbnail pressure test can help. Real gold dents or flattens. Mica crumbles or slides. UV light offers another quick filter. Though gold doesn't fluoresce, some minerals that mimic its look, especially certain feldspars or scheelite, do. Shining a long-wave UV lamp over a suspect sample might reveal unexpected glows. Blue-white for scheelite, yellow for calcite, even reddish for certain garnets. These are not negatives. Some of these minerals can co-occur with gold, but if your gold fluoresces, it's almost certainly not gold. All these tools, magnet, UV, streak plate, don't require much weight or cost, yet they massively increase your accuracy in the field. Each one filters out another layer of guesswork. And once a sample passes all these initial checks, density, magnetism, and crush test, it's worth moving up to the next level of testing. That's where conductivity enters the equation. Because unlike most imposters, real gold doesn't just look different. It behaves differently under heat and current. Gold is an exceptional conductor of both heat and electricity, and this trait becomes a decisive filter when visual tests leave room for doubt. Among all field-accessible methods, thermal conductivity testing offers one of the clearest lines between true metal and imposter, particularly in crushed or embedded forms where gold's appearance is partially obscured. While laboratory-grade meters are precise, even simple thermal pens, often used for diamond testing, can help rule out common mimics. To apply this test in a field setting, place the suspected particle or metal-rich area of a rock against the probe tip of a thermal conductivity tester. If gold is present and the surface is clean, the instrument will register a rapid heat transfer. Unlike pyrite or mica, which insulate or lag in response, gold absorbs and diffuses heat instantly. The reaction is near immediate. But beware, surface contamination like dirt or oxide coatings can affect results, so always expose a fresh, clean facet of the material. Streak testing provides another classic method for distinction. Use an unglazed ceramic tile, typically available at hardware stores, and drag the mineral across its surface. Gold leaves a soft yellow streak. Pyrite, despite its shine, leaves a dark greenish-black mark. This difference is striking and unambiguous, but again, it works best when the gold content is visible or at least accessible. If it's locked within quartz or sulfide, you'll need to liberate it first through fine crushing. Electrical conductivity, while less often tested in the field, adds another line of evidence. Real gold conducts electricity exceptionally well. Moissanite, a common imposter in gem testing, also conducts electricity, which is how diamond testers distinguish between the two. For gold, a multimeter can suffice in a pinch. Scratch a path to expose metal and test continuity. A strong signal across even a small particle confirms metallic conductivity, though not gold specifically. It must be cross-checked with density and streak. These physical behaviors, thermal absorption, electrical flow, streak color, aren't just scientific curiosities. They're tools for certainty in a field full of doubt. Because once a specimen has passed these hurdles, it's no longer in the realm of guesswork. It deserves to be treated as a serious candidate for further extraction. And that's when gravity takes the stage, literally. Because the best, most consistent way to prove a particle is gold is to weigh it in water, compare it to its dry weight, and watch physics confirm what eyes alone can't. Gold's density is unmistakable, more than 19 times heavier than water and significantly denser than nearly all rock-forming minerals. This property makes it one of the most reliable indicators of authenticity, especially when dealing with small flakes or embedded grains that might still look ambiguous. While you don't need lab equipment to leverage this trait, a basic water displacement setup could deliver surprisingly precise answers. Start with a small digital scale accurate to 0.01 grams, a narrow graduated cylinder or dropper tube, and a piece of wire or mesh to suspend the sample. First, weigh the dry specimen in air. Then fill the cylinder with water and record the starting volume to the nearest 0.1 milliliter. Carefully lower the sample, tied with thin thread or resting in a mesh, so it is fully submerged without touching the sides or bottom. Record the new water level. The difference in volume, in milliliters, equals the displaced water, and since 1 milliliter of water equals 1 gram, you can now calculate specific gravity using the formula. Sg equals dry weight / dry weight submerged weight. For example, if a sample weighs 1.02 grams dry and 0.73 grams when submerged, its specific gravity is 1.02 / 1.02 to 0.73 equals 1.02 / 0.29 almost equals 3.52. This would align with pure gold. Sg is almost equal to 19.3, only if the entire sample is metallic. But when testing or concentrate, expect lower values unless the sample is gold-rich. A reading near 3.5 may suggest quartz or sulfide-rich rock. 5 to 6 indicates heavy mineral content, perhaps galena or barite. 10+ signals dense metal inclusions, possibly gold. Even a small deviation from the 2.65 baseline of common rock is telling. Gold's signature density is what makes it settle in sluices, hug the bottom of pans, and resist turbulence that sweeps away lighter grains. You can also dry pan, a variant of this principle used in arid regions. Crush the sample and toss it gently in a wide, shallow pan. Tap rhythmically, and you'll see lighter particles rise while heavies concentrate in the center. Gold, if present, will roll reluctantly, hugging the pan. This behavior is consistent across grain sizes, which is why dry washing and gravity tables remain relevant even in the age of chemical leaching. But if your sample passes the gravity check and you're seeing dense, gold-colored particles that match streak, conductivity, and pan behavior, congratulations. You've cleared the most common traps. What's next isn't guessing, it's grinding. Because until the gold is fully liberated from its host matrix, you won't know what you really have. And that's where the crushing circuit begins. Jaw to disc, coarse to powder. Breaking rock is one thing. Liberating gold from it is another. Even visibly mineralized or may yield nothing until it's reduced to the right particle size. That's why professional recovery always begins with a crushing circuit, a sequence of mechanical reductions that expose and separate gold from the stubborn grasp of quartz, sulfides, or silicates. Here, size isn't just about convenience. It directly impacts how much gold you can recover and how efficiently. The typical progression starts with a jaw crusher. This device mimics a powerful bite, clamping rock between a fixed and moving plate until it fractures. Output size from a jaw crusher can range from several centimeters to a few millimeters, good for field prep, but not yet fine enough for gold liberation. At this stage, larger sulfide nodules may still contain locked gold, and quartz fragments might be gold-bearing without exposing any metallic face. Next comes the secondary crusher, often a roll mill or hammer mill, which crushes the jaw output down to sand-sized grains or finer. This is where early liberation starts. In some cases, free milling gold will begin to appear, tiny particles flaking out from the crushed host, ready for gravity concentration. But unless the ore is unusually rich or soft, this still isn't enough. Many gold particles are microns in size, far smaller than sand grains, and remain locked inside sulfide lattices or microfractures. That's where pulverization enters. Using a disc pulverizer or ball mill, the material is reduced to a fine flour-like powder. We're now at the micrometer scale, fine enough for gravity tables, flotation, or chemical leaching. At this level, you're no longer dealing with rock in any practical sense. It's now a homogeneous feedstock for recovery, and how you process it depends on the type of gold present. It's worth noting that not all ores respond the same way. Free milling gold, which separates easily once crushed, is ideal. But sulfide-hosted or refractory gold, locked in pyrite or arsenopyrite, requires chemical liberation. Before investing in chemistry, always check for free gold first. A run through a sluice or blue bowl with pulverized or can reveal whether it's worth proceeding. If you recover meaningful gold through gravity alone, you may not need to leach at all. One warning: crushing and grinding generate fine silica dust, which is hazardous when inhaled. Always wear a proper respirator, P100 or equivalent, and work in a ventilated area. Silicosis is irreversible, and gold isn't worth your lungs. Once your material is powdered, classified, and tested, you face a decision point. Gravity recovery may get you 50 to 70% of the gold in some ores, but if the rest is chemically bound, you'll need to extract it by other means. And that's where centuries of experimentation have yielded two dominant, controversial methods: mercury amalgamation and cyanide leaching. Both work. Both extract gold that gravity can't touch. But only one is broadly legal, and the other may poison more than just the rock. Mercury amalgamation is one of the oldest gold extraction methods still in use, especially in small-scale and artisanal operations. Its appeal lies in simplicity. Crushed or is mixed with elemental mercury, which binds selectively with gold to form a soft, silvery amalgam. This compound is then heated to vaporize the mercury, leaving behind raw gold. The process is mechanically straightforward, but chemically and environmentally disastrous. Mercury vapor is highly toxic, and even small spills contaminate water, soil, and air with effects that persist for decades. In many countries, mercury use is now restricted or banned outright. It persists, often in remote regions without access to alternatives. The problem isn't that it doesn't work, it does, but that it works too broadly. Mercury binds to other metals and contaminants as well, reducing purity and complicating recovery. More critically, any gold embedded too deeply in sulfides won't bind unless first roasted, a process that releases sulfur dioxide and intensifies toxicity. Cyanide leaching, the modern industrial standard, is far more efficient and precise. Finely ground or is soaked in a weak sodium cyanide solution, which dissolves gold into a soluble complex. The solution is then filtered and treated, typically with zinc powder, Merrill-Crowe process, or activated carbon, CIP/CAL processes, to recover the gold. This method can extract over 90% of the gold from finely disseminated or refractory ores, making it a staple in commercial mining. But cyanide is also dangerous. Though highly diluted in most operations, cyanide spills have devastated rivers and ecosystems, leading to strict regulation and costly containment. Leaching must occur in lined, sealed tanks or pads with neutralization protocols, pH monitoring, and emergency spill systems. It's not a backyard method. Even small-scale miners using cyanide need permits, technical knowledge, and proper disposal systems to remain compliant and safe. In recent years, alternative leaches have emerged. Thiosulfate, halogens like chlorine or bromine, and glycine-based solutions offer promising, less toxic pathways, especially for ores that resist cyanidation. Thiosulfate is already used in some commercial operations, notably by Barrick Gold in Nevada, and is gaining ground for its safety profile and ability to treat copper-rich ores that interfere with cyanide. Yet these methods are more chemically complex and slower to act. For prospectors and microminers, the gap between field-ready and lab-grade remains wide. That's why gravity and flotation remain dominant in small setups. Anything to avoid chemical exposure or disposal liabilities. Whichever route is chosen, a strange thing happens during leaching. The gold disappears. Visually, the solution looks like water. The once visible particles dissolve completely, leaving no metallic trace, until forced back out by chemistry. That moment of reappearance, when invisible gold returns to solid form, is one of the most quietly dramatic steps in the entire recovery chain. And when it does return, it's no longer buried in stone. It's ready for the fire. In the final stages of gold recovery, chemistry gives way to heat. This is the realm of fire assay, the oldest and still most trusted method for verifying gold content. When flakes, amalgams, or leach residues are collected, there's only one way to know their true value. Melt them. Fire tells no lies. It separates everything, impurities, base metals, silicates, and leaves behind a concentrated bead of pure, testable metal. The process begins with drying and weighing your collected gold-bearing residue. If the source is gravity concentrate or leach precipitate, you'll first mix it with a flux, typically a blend of borax, soda, ash, silica, and lead oxide, litharge. This flux lowers the melting point of the sample, collects base metals, and separates impurities into a glassy slag. The critical step is fusing the mix in a crucible inside a furnace, usually at 1,000 to 1,100 degrees Celsius. As the material melts, two things happen. Base metals bind to the lead, which acts as a collector, and everything else either floats as slag or is left behind. Once cooled, the slag is cracked off, and the remaining lead button is placed in a small cup made of bone ash, a cupel. In a second, hotter fire, the lead oxidizes and is absorbed by the cupel, leaving behind a bead of gold and possibly silver. That bead is your proof. It may be smaller than a lentil, but it carries absolute weight. At this point, it can be reweighed, chemically tested, or even refined further using aqua regia, a mixture of nitric and hydrochloric acids that dissolves gold selectively, allowing high purity recovery. This is the moment where theory ends and quantification begins. You now know exactly how much gold your rock held, down to the milligram, and the number surprises many. A few grams per ton, G/T, is enough to justify commercial interest. Anything over 10 grams per ton is potentially high grade. Over 30 grams per ton, inaccessible, or that's exceptional. But even 1 gram per ton can be viable in scale, especially if it's free milling and the host rock is soft. For artisanal operations or serious prospectors, this step is the pivot point. It's where decisions are made. Continue processing, scale up, seek permits, or walk away. Because no matter how much effort went into crushing, panning, or leaching, the assay bead tells the final truth. Still, not all samples need full assay. Many times, visible gold and solid concentrate recovery are enough to justify bulk sampling or field-scale processing. But once you have that bead, you've crossed from prospecting into extraction and from theory into economy. Yet even the purest bead raises a question no lab can answer. Where did it come from? Because origin, not just purity, can mean the difference between commodity and collectible. And that depends entirely on geology. Gold doesn't occur randomly. Its presence, especially in extractable concentrations, is dictated by the ancient architecture of the Earth. That's why understanding the host geology is as critical as any field test. From the earliest placer finds to modern hard rock mining, the most productive discoveries have occurred within predictable structural environments. And once you've identified gold in a rock, your next job is to trace its source. Not just to find more, but to determine if your find sits within a larger, economically viable system. 3 geologic environments dominate gold discovery: greenstone belts, volcanic arcs, and structural shear zones. Each forms under different tectonic conditions, but they share key traits: heat, pressure, hydrothermal fluids, and structural conduits for mineral deposition. Gold doesn't form on its own. It precipitates when metal-rich fluids cool or chemically react with surrounding rock, usually along faults, fractures, or lithologic boundaries. Greenstone belts, ancient volcanic sedimentary terrains often over 2.5 billion years old, host some of the richest gold deposits on Earth. Found in regions like the Canadian Shield, West Africa, and Western Australia, these belts consist of mafic to ultramafic rocks altered over time by regional metamorphism. Within them, quartz carbonate veins, shear zones, and iron formations are prime gold targets. If your sample came from a belt like this and tests positive, you may be on the edge of a lode system. Volcanic arcs, especially those near subduction zones, produce a different style: epithermal and mesothermal veins. These systems often occur in younger rocks, less than 100 million years old, rich in silica and prone to intense hydrothermal alteration. Common in places like the Andes, the Philippines, and parts of the western U.S., these deposits can form bonanza-grade veins near the surface, sometimes with visible gold. In these settings, minerals like adularia, barite, and pyrite often accompany gold. Then there are structural shear zones, broad zones of faulting and crushing where rock has been ground down and altered by heat and fluid movement. These zones can act like gold highways, channeling fluids over vast distances and concentrating gold in multiple, stacked lenses. If your positive assay came from a fractured, altered rock in such a zone, you may be sitting on a larger target. These systems often show cerussite, chlorite, and iron carbonate alteration halos. Easy to miss unless you know the mineral signatures. Understanding your host geology not only informs extraction, it dictates value. Gold from greenstone belts often contains trace elements like tungsten or tellurium, which can enhance or hinder processing. Epithermal gold may come with high silver content, increasing market value, or with arsenic and antimony, complicating refining. In collector markets, gold from famed localities like Kalgoorlie, Timmins, or El Callao can fetch premiums simply based on provenance. But to claim a provenance, you need proof. That means tying your sample to a specific geologic structure, map formation, or known belt. Geologic maps, satellite imagery, and regional exploration reports become vital. If your find doesn't align with any documented belt, you might be looking at something new or at a stranded anomaly with no economic depth. And as your understanding deepens, so do the responsibilities. Because where geology concentrates gold, nature concentrates risk. Steep slopes, unstable cuts, and shifting water tables can turn a promising dig into a disaster. Before you go deeper, you need to assess not just grade, but safety. Gold might be heavy, but water moves it. And where gold collects, so do hazards. As prospecting shifts from curiosity to active recovery, digging deeper, trenching veins, or working creekside benches, the risk landscape changes sharply. Erosion, slope failure, flash flooding, and even legal exposure become real. No matter how rich the ore, an unstable site can erase the gains in seconds. Start with terrain. In placer zones, especially near creek bends or ancient terraces, gold accumulates where water once slowed, but these are often the same spots prone to bank collapse or undercutting. A false step near a gravel wall after rain can trigger a slide. Always evaluate the sediment. Is it loose, layered, and steep? If so, cut small support walls and never work alone. In hard rock zones, especially in shear zones and fault gouges, the rock can appear solid but be intensely weathered. Quartz-rich veins surrounded by clay-altered schist or greenstone are often structurally weakened. Chiseling or hammering without bracing can collapse narrow tunnels or pits. If your dig expands beyond a shallow trench, consider simple shoring with timber or plate. Safety used to be optional until it wasn't. Water is another silent danger. Even dry zones can flood quickly after distant storms. Seasonal creek beds, often rich in gold, can become torrents with zero warning. Before working in or near them, check upstream rainfall forecasts and recognize debris lines, the dark organic high water marks that show recent flood levels. Never dig below these without a solid escape path. Then there's chemical risk. If using any leach solution, especially cyanide, hydrogen peroxide, or thiosulfate, you must manage spillage, exposure, and disposal. These chemicals work in controlled environments, not tarps on dirt. Always mix small batches, wear gloves and respirators, and neutralize waste. Even simple borax flux used during smelting can cause serious burns if splashed or inhaled during ignition. Legal risk matters too. Gold may be found anywhere, but that doesn't make it yours. Know whether you're on private land, public land, or claimed territory. In countries like the U.S., unclaimed federal lands are open to prospecting under specific laws, like the 1872 Mining Act, but active claims, protected watersheds, and tribal lands are off-limits. In Canada, Australia, or South America, permit structures vary, but collecting without permission can mean seizure of equipment, fines, or worse. Finally, consider weather windows. Some of the richest field zones are only accessible for a few months per year. Snow melt, monsoon onset, and heat waves can all shut down recovery. Even lab testing isn't immune. Assay queues often spike in late season as operations rush to finalize claims. If you're serious about verifying or scaling up your find, align your sampling and submission timeline early. Because once the sample grid is in and the test suite run, the next step isn't digging, it's confirmation. Field results are promising, but they must hold under repetition. Only then can you justify cutting deeper, chasing veins, or preparing a claim. And for that, you need to prove more than potential. You need repeatability. Repeatability is what separates a fluke from a deposit. A single promising pan, bead, or assay might ignite interest, but unless the results can be replicated, grid confirmed, and mapped across a wider area, there's no basis for development. In the real process of extracting gold from stone, proof doesn't come from one hit, it comes from pattern. And establishing that pattern means executing a disciplined, low-bias sampling strategy over terrain that hides more than it reveals. This starts with gridding. Once a gold-positive outcrop or float sample is confirmed, you lay out a systematic grid over the surrounding area, typically using 10-meter, 20-meter, or even 50-meter spacing, depending on terrain and accessibility. At each grid point, a sample is taken from consistent depth and volume, crushed, and panned or assayed in the same manner as the original. The goal is not maximum recovery at each point, it's data continuity. You're looking for trends in grade, not just isolated highs. Marking each point with GPS, flagging, and depth notes creates a sampling map that, when plotted, shows gold distribution across the site. Clustering of results helps define or shoots, strike direction, and dip, key data when deciding whether to trench, drill, or scale back. A tight cluster of values above 3 grams per ton may justify mechanical recovery. Broad scatter under 0.5 grams per ton likely doesn't. But grid sampling also prevents confirmation bias, the trap of sampling only good-looking spots. It forces the data to speak objectively. Many would-be miners skip this step, preferring optimism over statistics. But a pattern of repeatable recoveries, especially when cross-tested by panning, gravity, and assay, gives you the leverage to justify larger investment. It's the only real way to predict total recoverable gold from a zone. At this stage, many operators also run bulk samples, processing larger volumes, 50 to 500 kilograms, through gravity methods or flotation to simulate real throughput. These not only confirm average grade, but help evaluate recovery efficiency and tailings loss. If a bulk test returns significantly less gold than expected from assay data, your liberation method may need adjustment, or your ore is refractory and needs chemical extraction. Consistency also matters for verification. Labs often test using fire assay, ICP, or atomic absorption methods, but results vary with particle size, digestion technique, and and lab skill. Submitting duplicate samples to different labs, or even sending blind duplicates under separate names, is a time-tested way to catch variance or errors. Professional operators budget for this, because one bad assay can mislead an entire project. Once repeatability is demonstrated, you've moved from speculation to evaluation. The error isn't just interesting, it's quantifiable. You know grade, host rock, recovery method, and spatial spread. The next step isn't necessarily digging deeper, it might be deciding how to monetize. Because gold and rock has many futures, process it yourself, sell it raw, partner with a mill, or lease the claim. Each option has trade-offs, and the right one depends not on sentiment, but on market reality. Gold might be timeless, but its value is never fixed. Once confirmed, quantified, and repeatable, the question becomes one of market alignment. How much is your gold worth, in what form, and to whom? Because not all gold is created equal. Flake, nugget, dust, or embedded ore each carries a different price point, processing cost, and buyer pool. And choosing the wrong path can mean losing 30 to 50% of your value before you even get paid. Start with form. Nuggets, especially those over 1 gram, often fetch premiums over spot price due to rarity and collector appeal. Well-shaped, naturally smooth nuggets can sell for 10 to 30% more than their melt value if documented and photographed properly. In contrast, flour gold, fine flakes under 0.1 millimeters, trades at steep discounts due to difficulty in refining and measuring purity. Most buyers will deduct 10 to 25% for handling and loss risk unless it's already smelted. Concentrates, black sand or sulfide-heavy material containing visible or assay-confirmed gold, require more nuance. Most refiners will pay based on estimated recoverable gold, not total weight. Unless you've already performed a fire assay and can guarantee gold per ton, expect offers that factor in both processing loss and risk. A typical deal might involve 70 to 80% of the estimated gold value after deductions for moisture, impurity, and smelting cost. Or rock itself, even with confirmed gold, is rarely sold as is unless in very high volumes. Small batches with visible gold may attract mineral collectors, museums, or jewelers looking for display pieces. But these markets are niche, slow-moving, and selective. For commercial sale, you'd need scale, dozens of tons with consistent grade and logistics for haulage to a processing facility or buyer's site. Then there's purity. Raw gold from field recovery often contains silver, copper, or trace elements. Most natural gold ranges from 70 to 95% purity, and this affects price directly. If your smelted bead tests at 82% gold, you're only paid for the gold content, unless you refine it to 0.999, which adds cost, time, and certification requirements. Independent assayers or refineries will provide a settlement sheet breaking down deductions, metal content, and payables. Market timing matters too. Gold price can swing $50, $100 per ounce within weeks, driven by currency movements, geopolitical tension, or investment cycles. Selling into a low market means leaving value behind. Yet waiting too long risks storage costs, theft, or missed liquidity. It's often wiser to sell in tranches or lock prices via futures if you're dealing at volume. Finally, the buyer type affects everything. Local gold shops pay quickly, but at steep discounts. Jewelry buyers often want refined or specific forms. Private collectors may pay premiums, but require trust, documentation, and patience. Licensed refiners offer transparency, but may require minimums and lengthy settlement periods. This is where paperwork helps. A gold recovery backed by grid samples, photos, lab results, and provenance data isn't just more credible, it's more valuable. Buyers trust data, and trust adds percentage points. But where trust is abused, there are losses. Because for every honest buyer, there are also middlemen who exploit field finds, underpay, or pass off fakes. To protect what you've recovered, you need not just tests, but defenses. And that's where fraud prevention begins. The gold may be real, but that doesn't mean the deal is. Across every step of extraction, from concentrate sale to assay submission, fraud remains one of the most persistent threats to independent miners and field operators. Some losses are subtle: underreported assays, excessive smelting fees, manipulated weights. Others are brazen: fake buyers, swapped samples, or counterfeit gold entering the trade stream. To protect your recovery, you need not just technical knowledge, but transactional discipline. And it starts with understanding the most common traps. The underpricing trap is the most pervasive. A buyer tests your sample, perhaps with a magnet, loop, or acid, then declares it low grade or mixed, offering half of spot. Unless you've performed your own fire assay or specific gravity check, you're negotiating from ignorance. Always test independently before showing product. And, if possible, accompany your material to the buyer's lab. Request a copy of the assay sheet and compare it with known standards. Reputable refiners provide itemized breakdowns of deductions. If you're quoted a flat discount with no documentation, walk away. Sample switching is another field-level scam. A buyer or third party handles your ore or concentrate briefly, then hands you back a different container. This is especially risky during transport or storage. Always seal and mark your samples with tamper-evident tape. Use coded labels and photograph the container before and after transit. For bulk deliveries, sign and countersign weight sheets at loading and offloading, and avoid letting product out of sight until verified. Then there's fake gold, not sold to you, but used to lower your offer. This happens when unscrupulous buyers claim your material is brass, gold-plated lead, or a high-index simulant. To defend against this, run basic field tests before showing. Nitric acid for base metal reaction, streak test for true gold color, and conductivity test for non-ferrous behavior. True gold won't fizz, flake, or streak dark. Even showing these pre-tests during negotiation can raise your leverage and filter out scammers. In smelting contexts, overweighing flux is a hidden cost. If your concentrate is mixed with large amounts of flux, especially lead oxide, borax, or soda ash, without proper documentation, your gold yield may be reduced on paper even if it's unchanged in fact. To avoid this, ask for a pre-weighed flux mix and witness the smelting if possible. If smelting offsite, always retain a split sample from your original concentrate for third-party verification. Chain of custody integrity is vital. From field to furnace, keep a log of who handled what, when, and where. Label samples with waterproof, indelible markers. Photograph with scale, GPS, and date tags, and maintain duplicates whenever feasible. These steps not only protect against fraud, they strengthen any future claim you might register or defend in court, arbitration, or regulatory disputes. Finally, watch for market informals. Buyers who operate without licenses, issue no receipts, or offer cash-only deals. While tempting, these expose you to legal risk, especially if local laws require proof of origin or export permits. Even if the gold is real, selling it improperly can make it legally worthless. Avoiding these traps means more than keeping what you earned. It preserves your right to mine, sell, and build. But to truly close the loop, you need one final piece: side-by-side evidence. A suite of test results, visual matches, and physical proof that no buyer, regulator, or partner could dispute. And that evidence begins not in the field, but under controlled repetition, side by side. Side-by-side testing is the final filter, the crucible of certainty where everything that seemed probable is either confirmed or dismissed. In gold extraction, especially from hard rock, parallel testing under controlled conditions is what turns isolated results into proof. It's not just about confirming presence. It's about eliminating doubt, fraud, and error. And it's the step where you stop making claims and start showing them. The methodology is straightforward but rigorous. Start by selecting at least 2 representative samples from your test grid, one that showed promising gold presence and one that did not. Process both identically, same crushing size, same pan or gravity setup, same drying time, same water source. This side-by-side format immediately shows behavioral contrast. If one pan leaves gold and the other doesn't, your field indicator to line. If both behave the same despite earlier visual clues, it's time to reevaluate your sampling logic. Next, move to lab validation. Submit split samples from the same crushed batch to 2 separate assay labs, preferably using different test methods, e.g., fire assay versus ICP-MS. The goal isn't redundancy, it's cross-confirmation. Consistent results across labs mean your findings are robust. If values diverge, you've uncovered an error source, sample prep, contamination, or instrumentation, and can dig deeper. One of the most telling side-by-side tests involves pre- and post-leach concentrates. Take a high-grade pulverized sample, divide it, and run 1/2 through gravity only. Reserve the other for leaching. After processing, weigh both recovered gold amounts and compare to the total assay value. If gravity recovers 60% and leach another 30%, you've now mapped the ore's processing profile. If one method underperforms, the side-by-side tells you where the loss occurred: liberation, recovery, or measurement. A similar logic applies to magnetic separation. Run a magnet over one split of your crushed sample and leave the other untouched. Process both. If recovery improves without magnetic material, you now know your gold is not magnetically associated and may be free milling. If recovery drops, some of your gold may be in magnetic sulfides like pyrite or arsenopyrite, requiring different processing logic. Even visual proof has a role. Photograph each pan or sluice output under consistent lighting, with scale indicators and labels. Document particle size, distribution, and luster.